Hey everyone! So today we're going to get into something really fascinating. It's a discovery that kind of peeks behind the curtain at how a new type of AI language model actually thinks. And more importantly, we're going to see how this single insight led to a super elegant, simple way to make these models way, way faster without losing any quality.
So let's just start with this question. What if an AI model solved a problem, found the right answer, but then just kept going, burning through a ton of time and energy on something that was already done? I mean, it sounds pretty inefficient, right? Well, it turns out this is exactly what's happening inside a really promising new class of AI called diffusion language models.
Okay, so let's break this down. To really get why this is a big deal, you have to know about the two main ways these things work. On one side, you've got your auto-regressive models. Think of a lot of the GPTs we all know and love. They work step by step, generating one word at a time, just like writing a sentence. But then you have these diffusion language models, or DLMs. They're built to be parallel. They generate all the words at the same time. It's kind of like a sculptor who starts with a rough block of clay and slowly refines it until a perfect sentence emerges.
Now you'd think that sculpting approach, being all parallel, would make DLMs way faster. I mean, that's the whole point, right? But here's the paradox. In the real world, they are often slower than the old word-by-word models. And this has been a huge headache for researchers and developers trying to use their unique abilities.
So what's the holdup? Well, there are a few techie reasons. For one, they can't use common speed hacks like KV caching, which helps other models remember what they've already figured out. And their whole method of looking at the entire sentence at once, that's called bidirectional attention, it's just really computationally heavy. But the biggest issue, and what we're really focusing on today, is that they need a lot of these refinement steps to get to a good answer. With every single step, the model takes its messy, noisy text and tries to make it just a little bit clearer and clearer and clearer until it finally gets to the end.
But this is where the research we're looking at today has a real breakthrough moment. By actually digging into those refinement steps, the authors found this powerful, totally overlooked thing they call early answer convergence. Basically, the model knows the right answer long before it's actually supposed to be finished. Which, of course, makes you ask, okay, how early are we talking? At what point in that long chain of refinements does the model secretly lock on to the right response while it's still pretending to be working on it? Well, the answer is surprisingly early. And the data here it's just wild. Look at this. On a tough math benchmark, the model had already internally figured out the correct final answer 88.5% of the time when it was only a quarter of the way through its process. By the halfway point, that number is over 97%. This means that for almost every problem, the model is just spinning its wheels for the entire second half of the process, doing absolutely nothing useful. The paper itself puts it perfectly. They say there's, and I'm quoting, a strikingly high proportion of samples can be correctly decoded during the early phase, which, they continue, underscores a fundamental redundancy in conventional full-length slow decoding. So this isn't some small inefficiency. No, it's a deep, fundamental waste of effort that's baked right into the process. So if the problem is that the model is just running on and on because it doesn't know when to stop, well, the solution is to tell it when to stop. And this simple idea led the researchers to create a really clever training-free method they call Prophet.
The big idea behind Prophet is a strategy called early commit decoding. So instead of just letting the model run for a fixed number of steps, say 50 steps every single time, the system is now actively watching the model's own certainty level at every step. And then it makes a smart on-the-fly call about whether the answer is good enough to stop.
But how does it know? How can it possibly measure certainty? Well, it uses this beautifully simple little metric called the confidence gap. For every single word in the sentence it's building, the model looks at its number one best guess and its number two best guess. The bigger the gap in confidence between those two options, well, the more certain the model is that its top choice is the right one. Simple as that. And this sets up a really simple, elegant little loop. At each step, first the model makes his prediction, then Prophet steps in and checks the average confidence gap for the whole answer. If that gap is wide enough, meaning the model is really sure of itself, boom, it stops and spits out the answer. And if it's not sure yet, it just does one more refinement step and checks all over again. And this comparison just shows it all. The standard way just plods along for all 10 of its required steps, even though the answer was totally stable back at step 6. Those last 4 steps, pure wasted computation. But Prophet is smart. It sees the answer has settled down at step 6, it confidently stops the whole process, and in this case, it saves over half the work. Okay, so that all sounds fantastic in theory. But
Does it actually work in practice? Can you really just chop out half the steps and not screw up the quality of the answers? Well, the results pretty much speak for themselves.
And yeah, the results are really impressive. On the MLU General Knowledge Test, Prophet got a 2.34 times speedup with basically the exact same accuracy. On that hard math test, a 1.69 times speedup with a tiny 0.3% dip in accuracy. But then look at a complex planning task like Sudoku. It kept the exact same accuracy while being an incredible 3.4 times faster.
I mean, a 3.4x speedup on something as complex as Sudoku? That's a total game changer. And remember, this is achieved with a simple method that requires zero retraining. It's like a wrapper you can just put around your existing models without any expensive fine-tuning. That's huge.
So let's wrap this up with the big takeaways for anyone building this stuff. First, this redundancy isn't a small thing. It's real and it's significant. These models are wasting a ton of compute. Second, that confidence gap idea turns out to be a really simple but super effective way to know when an answer is baked. And third, and maybe most importantly, this all means we can get massive speedups without the usual trade-off in quality, and, crucially, without any expensive retraining.
And that kind of leaves us with one last big thought to chew on. This whole discovery feels like we're just pulling back the curtain a tiny bit on how these models actually think. And if they're solving problems this early, this efficiently, just under the surface, it really makes you wonder, what other hidden behaviors, what other massive efficiencies are just sitting there, waiting for us to find them inside these incredibly complex systems? Thanks for tuning in.